For 10 million years, this star has burned without stopping. Tonight, it stops. This red supergiant, 700 times the diameter of our sun, is dying, and we are witnessing its final hours. Its surface already trembles, unstable, because something deep inside has changed forever. But it was not always like this. 10 million years ago, this star blazed as a brilliant blue giant, 20 times the mass of our sun. Now it has already shed several solar masses into space. The end is closing in. To understand what is happening, we must go inside through the photosphere into the convection zone of a dying star. The first layer we encounter is the hydrogen-burning shell still alive with fusion, still fighting. Below that lies the helium shell, where 3 helium atoms fuse into carbon, forging the next element. And so it continues. Each shell fuses a heavier element, layer upon layer, all the way down to the iron core. Now we reach silicon, burning the very last fuel this star will ever have, and it is almost exhausted. At the center sits the iron core, the size of Earth, and it produces no energy at all. That iron core is still growing, feeding on the shells above it. It is nearly at the point of no return. Every fusion reaction before iron releases energy. Iron releases nothing. So what is holding this iron core up against the crushing weight of the star? And how much longer can it last? It is held up not by fusion, but by quantum mechanics alone, by the pressure of electrons refusing to be squeezed further. But now the iron core has reached its maximum possible mass. That electron pressure is failing. The Chandrasekhar limit is crossed. What happens next takes just 1/10 of a second. The core collapses from the diameter of Earth to just 20 kilometers in that single 10th of a second. In the same instant, 10 to the 58th neutrinos burst outward at the speed of light, flooding the universe. The shockwave from the collapse travels outward, triggering explosive nuclear burning in every shell it crosses. At the collapse center, a proto-neutron star is born, the densest object in the known universe. But high above, the star's surface doesn't know yet. The light from its own core's death hasn't reached it. Even the shockwave itself is now stalling, losing energy faster than the neutrinos can replace it. Then neutrino heating wins. The shockwave revives and resumes its outward drive toward the surface. 2 hours pass. The shockwave is nearly at the stellar surface, racing toward final breakout. The surface is brightening, expanding outward as the shockwave closes in from below. In just 10 seconds, more energy has been released than our sun will emit in its entire 10 billion year lifetime. Shock breakout. The surface temperature explodes from 3,000 to 50,000 Kelvin in an instant. From outside, the star has just brightened 10,000 times over in mere minutes. The stellar material is now expanding into space at 10,000 kilometers per second. Among the fresh debris, radioactive nickel-56 has been forged, and it will power the afterglow for months. By day 1, the supernova is 10 billion times brighter than the sun. At its peak, this single stellar death outshines an entire galaxy. Months later, the ejecta cloud stretches hundreds of billions of kilometers wide, still glowing from that nickel decay. The surface that didn't know is now gone. The star knew in its final second. At the center of the wreckage remains a neutron star, just 20 kilometers wide at 100 billion Kelvin. From its magnetic poles, twin particle jets launch into space at nearly the speed of light. Inside these jets, particles are accelerated to 99% of the speed of light. This newborn neutron star pulses once per second, with the precision of an atomic clock, a pulsar. 5 centuries pass. The ejecta cloud has become a glowing supernova nebula. These shining filaments are the actual atoms of the dead star, still glowing centuries after the explosion. Over millions of years, those atoms will drift outward and be recycled into new stars. Thousands of years later, the pulsar is slowing, winding down toward its own silence. And here is the profound truth. Every single atom of iron in the universe was made inside a dying star like this one. Every supernova seeds the galaxy with the building blocks of future worlds. This is what a supernova looks like 1,000 years after the explosion, a luminous grave still shining. At its center, the neutron star continues to feed the glowing cloud around it with pure spin energy. A 20-kilometer object, powering a 100-light-year-wide cloud with nothing but rotation. This nebula, the grave of one star, will glow for thousands of years before it finally fades. Even now, the energy trapped in this cloud exceeds our sun's entire output for 1 billion years. One supernova produces more heavy elements than the sun will generate in its full 10 billion-year life. Every single atom of iron in the universe was forged in a stellar death exactly like this. Calcium and oxygen, silicon and sulfur, all of it made inside a star. 5,000 light-years away, this supernova is bright enough to cast shadows on neighboring nebulae. From across the galaxy, every supernova shines as a beacon, a star's final gift of light and matter. 10,000 years later, the nebula fades, expanding until it vanishes into interstellar space. But its atoms drift outward, seeding the galaxy with the building blocks of future stars. Stellar death becomes the raw material of stellar birth, and the grand cycle continues. Of all the nebulae in the cosmos, which one moves you most? Drop your answer below. Right now, in our own galaxy, dozens of stars are preparing to meet the same fate. One red supergiant, just 600 light-years from Earth, is already in its final phase. When it finally detonates, it will blaze in daylight for weeks, visible across the entire sky. 1,000 years from now, a new nebula will bloom in that same patch of sky. That star will not simply die. Its atoms will go on to build 1,000 new worlds. Stars forge the elements. Supernovae deliver them to the rest of the universe. One iron atom, 5 billion years old, is about to become part of a new world. Somewhere in this galaxy, a new star is already forming from the ash of a dead one. The universe contains 2 trillion galaxies, each full of stories we haven't yet told. If this journey moved you, subscribe to Cosmic Depth, and we'll explore the cosmos together. If this changed how you see the cosmos, hit the like button and share this journey. Next week on Cosmic Depth, what happens when a star like our sun reaches its end? Thank you for taking this journey through the death and rebirth of a star. Keep looking up.